Hi, everybody. I've met a few of you at a couple of conferences over the past probably year and a half or so. For those of you who I have talked to, good to see you again. For those of you who I haven't, I hope to give you a few minutes update on what we're doing at Ryft. I first met with Steve Conway about a year and a half, 2 years ago, and IDC in general, of all the analyst firms, really impressed me, and because they really kind of understood the importance not just of HPC, but of high performance anything, right? And how best to kind of break away from the von Neumann stranglehold that is out there in the world today. And we can thank ourselves for that problem in a large degree, because some of the things that we do in HPC is still very von Neumann oriented, and that's part of the problem. What I'm going to talk to you about today is high performance analytics and the way we approach the problem. It is different. Whether it's disruptive or not, I'll leave up to you. We think it is. To piggyback on Steve's comment about our background, we came out of the intelligence community. We've been doing it for about 20 years. They bought our stuff and not other people's stuff for a reason. Our challenge was, how do we take this same interesting technology, non-von Neumann technology, out of the intelligence community and into the commercial space? And it has been a challenge, but there are things that we did to simplify it, and I'm hoping that that will help some of you. So first of all, what is it that we do? We sell boxes. We're in the business of selling that box right there. It's actually on the table back there, so during lunch or afterwards, if you just swing by, I'll show you the architecture. It's got a plexiglass cover on it. I'm the VP of engineering there, so I'm not going to try to sell you anything. I will talk technology to you all day long. I love this stuff. So what is it? It is I believe it's a solution to a large percentage of commercial high-performance data analysis applications with longer-term benefits for traditional HPC computing, potentially. So what do I mean by that? Well, what we've done for the government and what we're trying to do for the commercial space is we've identified some pretty significant bottlenecks, and we just try to eliminate them. It's really that simple. In the same way a programmer might, if he's smart, will profile his code and know where to optimize, we looked at the holistic entire system and said, how do we optimize this? And like we've heard from everybody here at this conference and every conference we've all ever attended, one of the biggest bottlenecks is the network. How do I eliminate that bottleneck? I don't use it. If I can fit everything in one box, I don't have anywhere to send the data. I don't got to go anywhere else. I'm all intranode at that point. So for a certain class of problems, if I can fit everything I need in that one box, then I don't have a network bottleneck. I don't have an I/O bottleneck. I probably don't even have a compute bottleneck if I do it right, if I'm not using von Neumann architectures. That's what we do. That's the box. This little piece is right here. Whoops, if I use the right little pointer guy. Those are 8 cartridges of 6 terabytes of SSD for 48 terabytes in that 1U form factor, all striped together with 2 FPGAs. They're Xilinx FPGAs. Later, if we have time, or you can hit me at lunch, I'll tell you why I chose them over Altera. Those 48 drives, again, are striped directly to FPGA fabric, but they're presented to the user, and this is really the key piece, presented to the user as a standard Linux file system. Not HDFS, none of this crap that's in there out there today that really kills performance, but a raw native Linux file system. We're actually running XFS and open source Fuse to fuse that together. Now the beauty of that architecture is that a user already knows how to use a system. You don't got to learn any programming languages that you don't already know. You don't got to use any specialized compilers. We're using GCC, standard GCC. The libraries we provide are Linux kernel drivers. We use DKMS, simple stuff, all straightforward to install in any system. We ship with Ubuntu 14.04 LTS on that front end, and a user sees it as Linux. Now what we've done though is we've combined that 48 terabytes as a single Linux mount point that you can LS files on, VI files on, but then we also couple that data directly not just to the OS, but to other FPGAs that can then do computations in real time on all of that data while Linux is still doing all of its stuff at the same time. What that means is when I send an analysis job to the compute fabric in that same 1U box, it can get at my data either resident on those 48 native SSDs or data ingress from the network side simultaneously in real time. So I can do analysis on real-time streaming data and my data at rest on the drives simultaneously. The beauty of that is that I can keep all of my I/O, all of my compute inside that one node as long as my data fits in 48 terabytes or as long as my real-time network feeds are 10 gigabit, 40 gigabit, or InfiniBand. That's what we support today. Now my back-end compute fabric though can actually run, this is compute fabric in terms of solving an analytics problem like a fuzzy search or image analysis operations. So I'm talking about actual user throughput, not flops. Flops don't matter. Matters is solving a real world problem. That's what matters. And that's where I think the HPC community can really help get this stuff into industry, is stop focusing on the minutia of your speeds and your flops and even your processor speeds and your number of cores. How fast do you solve their problem? That's what people care about. They don't understand HPC, and as much as we might want to teach them, they're not going to listen to us. But they will listen to us if we say, I can solve your problem in 30 seconds, and today it takes you 3 years. They will listen to that. Because it's all in one box, the power costs are just amazing. We can literally replace hundreds to even thousands of compute nodes, not cores, but nodes. I can prove that to you. I can just show it to you. On our website also, we've got several videos that go through and show this, but for certain data analytics algorithms, we can run through these things literally in seconds. What would take you 6 hours on a 100-node cluster takes us 6 seconds on one box. How do we do that? We're implementing the algorithms directly in FPGA compute fabric. It's that simple. So to the D-Wave gentleman's point where he has one instruction, we have one instruction that we rewrite, recreate every time for every single job. It's very simple, very straightforward. It's not a von Neumann architecture. So we're not limited by bus widths. I'm only limited by the size of the FPGAs I put in there. I routinely run 2,000, 3,000 bits wide when I'm solving a problem. That's how I get massive performance in a very small form factor. Very different than traditional HPC where I'm using large clusters of individual x86 nodes. We do have one x86 in that box, one x86, and that's just to serve up Linux. All the computations that matter occur in the FPGA fabric. How much power do I take with this thing? Running at full power, 10 gigabytes per second of solving the user's problem. So if they have a 20 gigabyte file, it takes 2 seconds to solve their problem, literally, for some of these fuzzy search types of problems. 500 watts peak power compared to 100 or 1,000 nodes sitting in the cloud or on your premise. The beauty of this also is it's modular architecture. And because of that, we can do other cool things with it downstream. And again, if you look at the plexiglass, you'll see this. We're working on a smaller one of these right now, so you can fit it in your cubicle or your desk as opposed to in a data center. Interesting things there for the edge analytics. Lots of interesting needs to do HPC at the edge of networks where you can't go to a cloud. You don't have time to send your data up to a cloud, analyze it, send it back because it's too late. If I'm on an oil and gas platform and there's a massive sensor going off, if I got to send it to a cloud provider and get my answer back 15, 20 minutes, 2 hours later, I might already be dead. If I'm in a retail store and I'm trying to buy something in an aisle, or I'm being targeted by this company to buy something, and I send it to a cloud to get the data and to get the answer back. By the time I get the answer back in the store, I'm in a different aisle, or I'm already checked out because I hate shopping. So there's these real-time edge problems that you just simply cannot solve with traditional HPC techniques, but they need to, because you can't do it with these clusters at the edge. You can't put them out there. You don't have the power. You don't have the manpower. But all that's great. But really, it turns out to be there's two things that are important when you're trying to solve these problems in the real world, in my opinion. Number one is performance. It's got to be very, very high performance. We already have that. In spades, we've done it for 20 years for the government. That's why they buy our stuff. What we didn't have until this device, and why we failed until now in the commercial space, is because it was too hard to use. It was too hard to program FPGAs. It wasn't hard for me or people that know it, but for traditional computer scientists, they don't understand how to do that. We do. So what we did is we said, okay, well, we're just going to build all these connectors, open source every single one of them, so that you can actually use our box with your traditional ecosystems. And in the real world, that's things like Apache Spark. We never once actually supported Hadoop because, no offense to any Hadoop people in here, but it sucks. It is absolutely horrible for data analytics. If you're using it, stop. Go use Apache Spark. Thankfully, companies like IBM are getting behind it now too, which is good. It's beautiful because it allows you to do heterogeneous computing at a whim. So you can actually use CPUs, GPUs, FPGA-enabled devices, ASIC-enabled devices all day long with no problems. And there's a built-in architecture in Apache Spark now called preferred node architecture. And that allows you to actually point certain jobs at certain nodes of that cluster so that when Ryft does something really well, send that to us. When the CPUs do something well, send it to them. When the GPUs do something well, send it to them. I hope that eventually the cloud providers get on board with this stuff and start doing it this way, because if they do, then everybody wins, not just HPC, but the commercial areas as well. And again, we actually believe in open sourcing every bit of this, so that's what we've done. You can find all this stuff on GitHub. and on sparkprojects.org and whatnot. Every single interface we have is open source, because we're in the business of selling boxes, so it's in my best interest to make sure that you can use it very easily. That's all I have, and thanks for your time. I appreciate it. If you have any questions, please hit me up at lunch.